e vediamo, poi dirà se non c'è. Ok? Non è possibile. Non fa ancora. Okay, we start. We're going to start in a few seconds or minutes. Can you hear me at home?
Yes.
And can you also see the slides? I guess.
Yes, we see them.
But you cannot see myself, right?
Right.
Right.
Ok. Vediamo se. Questo è lo stesso messaggio che ho ricevuto l'altra volta quando poi la registrazione non funzionava. Okay, let's try again. Just a little try. Okay, let's try again. We are making a test with the volume. Sorry. Panotte me lasciano perdere. Dai. Ok. Adesso ci sono perché non lo uso più, no, è registro da qua. Okay. This is just to explain what I'm doing. Of course, we are trying to use the Panopto app to record the class, which in principle should be able to put at the end all the recordings into one folder associated to the course. But the point is that, not just based on my experience, but the point is that it doesn't work very well at the moment. Okay, so the point is that there are problems with the video, with the audio, because there are a lot of options to select, and there is a conflict with the Microsoft Teams. So what I'm trying to do again is to record the class traditionally. I am aware that some of you cannot have access to the video, because if you don't participate into that specific meeting, we should find a way to give you all the links, or to record autonomously these videos and distribute them to your mates. I don't know. I talked about that also with the course program director, Professor Anna Montini, and she shares my view. Okay, so this is a big problem that we have currently. So what I'm trying to upload the slides in advance. Every week or every 2 weeks, add the material that when there is some substantial change, add the material that I write directly in the class. So you have all the slides there. There are also the recorded videos. So I cannot do more than this at the moment. Okay, so I'm so sorry for that, because I would like to, but I can't. Okay, so for today, I'm again trying to register traditionally. Okay, to record traditionally. Thanks. Okay, so. Record. Okay. Now that should be larger, okay? So, okay, today I'm going to briefly recall the second derivatives and its applications to one variable functions, but next I would like to switch today already to two variable functions. By the way, they have been also introduced in the exercise class because we only want to point out that there is nothing different in the computation of derivatives and also elasticities. You will see it's exactly the same. And of course, two variable functions have derivatives that hold, provided that we assume that one variable remains constant, okay? But if we make this assumption, then all the rules are exactly the same as for two variable functions, one variable functions. Second derivatives and applications, in particular second order approximations near a point are also important. Okay, so let me just briefly recall these concepts. In principle, these concepts are part of the crash course, but since we are aware that crash course is just a crash course, it's very quick review of all the material. Many of you, some of you, have different backgrounds, maybe not mathematics backgrounds. So I want to review briefly all the concepts and ideas that I believe are most important, also to understand two variable functions. Okay, so what is the meaning of an increasing function of one variable? An increasing function is just a function such that if I take a value in the domain x2, which is larger than another value x1, okay, I obtain two values of the function that are basically in the same order, okay? If x2 is larger than x1, then f of x2 is larger than f of x1. Here, this is called a weak definition because it is larger or equal to, okay? Larger or equal to. In this case, we say that the function is increasing in its domain. For this kind of definitions, the domain is, for simplicity, it is assumed that it is an open interval because we must adjust these definitions if we are at the boundary points of the domains, in the case of closed intervals. But basically, the idea is the same. So what is the definition of increasing in a strong sense or in a strict sense? When we have greater than, rather than greater or equal to, okay? So if f of x2 is strictly larger than f of x1, then it is strictly decreasing. Symmetrically, we can define a function which is decreasing. I mean, I increase the independent variable because I move from x1 to x2, but what happens to the dependent variable? It decreases, okay? So the function is decreasing because f of x2 is smaller or equal to f of x1. In this case, we have a weak definition. So we just say decreasing. If we have a strong inequality, or strictly less than, then we say that the function is strictly decreasing. Basically, for an increasing function, the graph goes from, let's say, bottom left to top right of your screen, right? For a decreasing function, it goes from top left to bottom right, okay? Like this. These are graphical examples. I can already show you these examples. This is a strictly increasing function considered over this particular interval. This is a function which is decreasing, clear, but not strictly over this interval because there is, this is not by chance, there is a sub-interval in which it remains constant, okay? So this is decreasing, but not strictly. Both are examples of differentiable functions. So differentiable means that we can compute the derivative at any point of the interval, and the derivative is number, okay, a unique number. So basically, the differentiable means that the graph has no corners, okay, where there is a sudden change of the slope. Here is another example. Some students would say that this function is increasing, you see, over its whole domain. That's not true. We cannot say it is increasing over its whole domain because this is a typical function in which we have, for instance, a polynomial in the denominator. Okay, polynomial have roots, zeros, values of the variable by which from which the polynomial becomes zero. Okay, so we have a zero in the denominator. If x0 is one such values, we have a typical behavior like this. This is called vertical asymptote for one variable functions. And even if you see that, I mean, x0 is excluded, it's not part of the domain, even if you see that the function always increases basically in its domain, we cannot say it is increasing from minus infinity to plus infinity by considering this interval, because if you move the independent variable, for instance, from this point to another point after x0, you have a jump, downward jump of the function, okay? So this is not increasing, but we can say it is strictly increasing over each sub-interval, where it is defined, continuous, and differentiable, okay? This is a typical behavior when the domain is made up of the union of two intervals, because, for instance, the denominator becomes zero. This is a function which is non-continuous, you see, there is a jump here. Anyway, it is strictly increasing. Because even if you start from slightly before the jump and you move x in such a way that it is moved after the jump, you see that the value of f of x increases. So this is increasing, non-continuous, and of course also non-differentiable, because if a function is non-continuous, this is non-differentiable as well. Okay, so why focusing on increasing functions? Because we are going to talk about second derivatives now. The reason is that the second derivatives are the derivatives of the first derivatives, okay? And you see here that there is a strong connection. You will see that there is a strong connection between the sign of the first derivative and the fact that the function is increasing or decreasing. Okay? Similarly, there is a strong connection between the sign of the second derivative and the fact that the function is concave or convex. And the reason is that the second derivative is the derivative of the first derivative. Why is that? Look at this slide. For differentiable functions, so we are not, for instance, we are not in this case, not in the last case as shown before, not in this case, but for regular function like this one or this one, for differentiable functions, the behavior of f, whether it is increasing or decreasing, is clearly related to the sign of f prime, okay? F prime is a slope, the slope of the graph. Okay, so if f prime, the derivative, is non-negative for any x in this interval, let's call it domain, then the function is increasing over this domain, and vice versa. This means if and only if. So there is a strong, for differentiable functions, there is a strong connection between the sign of the derivative and the fact that the function is increasing or decreasing. If the sign is non-negative over the whole domain, the function is increasing over the whole domain. If the sign is non-positive over the whole domain, the function is decreasing over the whole domain. Okay? If we have in particular a derivative which is 0 over the whole domain, then the function is constant. Okay? So this is a characterization of increasing, decreasing, and constant functions for differentiable function. those from you who know the mean value theorem in calculus know that proving this is based on this very important theorem in calculus, which is called the mean value theorem. So, you see here that we are stating definitions in weak terms. If you want to have strong results, if and only if, we can only state definitions in weak term here. Derivative greater or equal to function increasing. Increasing also includes the case constant, okay? Weakly increasing, okay? It's not possible to write here if the derivative is strictly positive, then the function is strictly increasing. This doesn't hold. It doesn't it does only hold in weak terms. For instance, in strong terms, we have this. If the derivative is strictly positive, then the function is strictly increasing. But you see here, there is only this direction of the implication. I mean, it's not true in general that if the function is strictly increasing, then the derivative is strictly positive over the whole interval. That's not true. By the way, if the function has derivative which is strictly negative, then the function is strictly decreasing. So this is called, when you have this is called the necessary and sufficient condition. Necessary and sufficient. From left to right means sufficient. From right to left means necessary. Here, you have only a sufficient condition for a function to be strictly increasing. If the derivative is strictly positive over an interval, I can conclude that the function is strictly increasing over that interval. It's only sufficient. This means that there may be other functions that do not have this property, but they are strictly increasing as well. Is that clear? The difference between necessary, sufficient, and necessary and sufficient is quite important. And a popular example for a function, I don't want to waste time on this, on the proof, but it's clear that the cubic function, the elementary cubic function, y equal to x to the power of 3, as this graph, in particular has a slope that, let's say, at a unique point here becomes 0, but then it remains strictly positive, okay? If you consider this on the whole interval of the domain, which is minus infinity plus infinity, you see that the function is strictly increasing over the whole interval, because if you take a point, if you move from 0 to the right, so if you increase x, you also increase y, basically. But the derivative has one point where it's 0. So the converse implication is not true. A function can be strictly increasing, and at the same time, the derivative can be equal to 0, not over an interval, of course, but at a finite number of points in the domain, particular at one point in the domain. Okay. Second derivative and higher order derivatives. Here comes the important point of this initial part of today's class. Suppose that you have a function which is differentiable. For one variable function, differentiable just means that we can compute the derivative. And the derivative is a number. The derivative gives the slope of the graph. In order to be able to have a uniquely defined derivative at a point, okay, we must have a smooth curve, okay, because if we have a corner like this, clearly at this point we have two different slopes near this point, okay, one like this and the other like this. But derivative means a unique slope. Even if I slightly move my point to the left or to the right, I must arrive in the limit at a unique slope, okay? This is the main idea. But if our function is differentiable, then I can compare, you know, the derivative itself is a function of x, because it's the slope at a specific point of abscissa x. I can compute, in many cases, the derivative of the derivative, and this is called the second derivative of the function. at a generic point x. So conceptually, there is nothing different. The derivative is itself a function of x. If the derivative is a regular function, I can compute also its derivative. And this is called the second derivative of f. The same way, I can compute the third derivative, a fourth derivative, and so on and so forth. What really matters in applications to economics are the first derivative and the second derivative, because they characterize almost all the properties of a function that are useful for the basic application, okay, of the derivatives. What is the notation for the second derivative? This one, for instance, you have d, it's like d squared f over dx squared, and this comes from this, okay? df over dx is the derivative, or df by dx, okay, is the derivative. And this is the operator, d over dx is the operator for the derivative. If you apply the operator for the derivative to this function, which is already a derivative, it's like having twice d in the numerator and dx times dx in the denominator. Of course, this is not algebra. This is not a notational trick, okay? And this is the reason why it is written this way. Another way to write it is, the first derivative would be capital D f of x, and the second derivative is capital D squared f of x. This is not a square, it's only an order of differentiation. So the notation is really important. Just a few examples for very popular functions. This is the elementary power function with a constant, capital A, that multiplies a variable, which is called k here, to the power of alpha, where alpha in economic applications is very often between 0 and 1, can be 1/2, 1/3. The name of the variable is k because this is the most simple, let's say, model of production function in which it is supposed that there is only one production factor, which is the capital. So in many applications, this K could be the capital per unit of labor, okay? Okay, but basically the meaning is capital. This is a very popular production function in one variable when the model requires to have a unique input factor. We often find this production function. What is its first derivative? Is, we already know that, is alpha times A times K to the power of alpha minus 1. And the second derivative is, again, alpha times alpha minus 1 times, of course, the constant capital A times K to the power of alpha minus 2. So this is the first and second derivative of the elementary power function, written in a way that it recalls a production function. What about this? Just to show a couple of examples. This is the ratio between two polynomials of degree 1. If I want to find the domain of this function, I must be aware that the denominator can become 0 here, so I must exclude minus 1. It is any real number except minus 1. It's written in this way. The first derivative, this is the quotient, the rule for the differentiation of the quotient. So it is the derivative of the numerator times the denominator, which is x plus 1, minus the numerator x plus 2 times the derivative of the denominator, which is 1, over the denominator squared, okay? And, of course, if you simplify here, you obtain x minus x becomes 0, 1 minus 2 is minus 1 over x plus 1 squared. So we can, for instance, if we look at this derivative, we can be sure that the derivative is strictly negative over the whole domain. Be aware that the domain is not a unique interval, it's the union of two intervals, but in each of these subintervals, we will have a strictly decreasing function, okay, in each subinterval. What about the second derivative? The second derivative is the derivative of this one, so it is minus 2 times x plus 1 to the power of minus 3, which is, it changes its sign. It changes its sign over the domain, because when x is larger than minus 1, so in the upper subinterval of the domain, this is clearly positive, but in the lower subinterval of the domain, this is negative. So here we will have, you will see, we have a convex function over this interval, a concave function over this other interval. That's because the first derivative never changes its sign, but the second derivative changes its sign depending on the ranges in the domain. So why is the second derivative related to concavity or convexity? We must be aware of what is the definition of concavity, convexity, but clearly the sign of the second derivative. Remember that the second derivative is the derivative of the first derivative, okay? So the sign of the second derivative determines whether the slope of f, which is the first derivative, that is f prime of x, is increasing or decreasing. So when you compute the second derivative, and we see that the second derivative is positive over a certain interval, we know that the second derivative is the derivative of the slope, okay? So we know that the slope of that particular function over that interval is increasing. So the slope is increasing, okay? So you may want to see a couple of graphical examples. Maybe there are some examples also later, but okay, they are here. I can use these ones. Look at this function. What about the slope of this function? Here is negative. The slope is negative, okay? At the beginning of this interval, it is negative. Then it is again negative. But the value of the slope is less than at the beginning of the interval. Then it becomes 0. 0 is the slope of a line which is parallel to the x-axis. Okay? Then it becomes positive. Then it becomes positive, but larger and larger. It's more and more sloped. Since the slope is increasing, you see the typical shape of a convex function, okay? Upward concave means the slope is increasing. So this is increasing, and the function is convex because f prime, the derivative, is increasing. What about this one? It's in this interval we have always a positive slope, but here it is very steep. Then it becomes flatter and flatter and flatter. So the slope is positive, but it is decreasing. Okay? Decreasing slope means concave function. Okay? Concave function means concave downwards, like this. I hope this is clear. It's related to this, whether the slope is increasing or decreasing. Of course, you may see here a potential problem. So what about these functions that do not have a slope over the whole domain? I mean, it's functions that are not differentiable at some points. I don't want to go into details, but of course, concavity and convexity are more general concepts than those of the previous slide. You can have a look at the textbook to understand more. So typically we have also cases in which the function is not necessarily twice differentiable, means it doesn't have necessarily a second derivative in order to apply the test for concavity with the second derivative, okay? It may be a function like this. It's not even differentiable at this point. There is a corner, you see? So what is the definition of concave or symmetrically convex? You have the graph here of the function, and you have an interval where this function is defined. If the line segment you see the red line segment here, joining any 2 points of its graph. Any 2 points, I could have selected the points also here and here, for instance, okay? Any 2 points of its graph is below the graph or on the graph, then we have a concave function. For a concave function, just take any 2 points of the domain, join the corresponding points on the graph with a segment. If the segment is below the graph of the function, or as a limiting case, it overlaps to the graph, then you have a concave function like this. It's very intuitive. A function is convex if same definition, but the line segment lies above the graph. Okay. This is a slightly more general definition for concavity. This is not, of course, the most general definition, because it's interesting. It is intuitive geometrically, but of course it has a big limitation. This definition. It is limited to the case of one variable function. So what about defining concavity, convexity for a function, the graph of which is not a curve in the plane, but is a surface in the space, okay? It's very difficult to define it, to use this definition, okay? We have a more general definitions for this. And the more general definition, which is, it is important to give, this is maybe one of the few pieces of theory in this course, but it's just ideas, definitions, it's not proofs, not theorems. Just precise ideas, precise definitions, okay? And a more general definition of concavity or symmetrically convexity builds on the concept of a convex set. So this is based on set theory, okay? If you have, you remember the usual representation for sets, okay? Take this one. For instance, this is a subset of the plane, okay? But you can do the same also for a subset, a kind of ball in the three-dimensional space, or another volume in the three-dimensional space. This set in the plane is a convex set. And this set in the plane is not convex, is a non-convex set. So what is the definition of a convex set? Set means all the points included here plus the boundary, right? Take any 2 points that belong to the set. Join them with a segment. These sets are subsets of the plane and not generic set, okay, of elements. Just subsets of the plane. Join them with a line segment. If the line segment lies entirely into the same set, then the set is convex, okay? And the point is that here, for instance, you can find points, like the 2 red ones. If you join them, you have a segment that is fully included in the same set. But if you join these 2 points here, there is part of the segment which is not included in the set anymore. So this is not a non-convex set. This is convex. So the definition is that a subset A of the plane, R squared is the plane, is a convex set if the line segment joining any 2 points of A is totally included in A. If we define properly a convex set, then we can arrive at a general definition of a concave function. Why? Function f of x is concave if the set capital A of the points belonging to the plane, because you represent the function in the plane, right? If the set A of points xy that belong to the plane, such that y is less or equal to f of x, is a convex set. And symmetrically, we say that the function f is convex if it's negative minus f is concave. So there is no need to define a convex function. When we add the definition of a concave function, if we know that the function is concave, it's negative, it's convex. So what is the meaning of this definition? What are the points of the plane such that y is less or equal to f of x? Are those points which lie below the graph of the function. Because y equal to f of x is the graph. Y less or equal to f of x means that the vertical coordinate is smaller than the one needed to be on the graph, right? It's smaller, so it's below the graph. Here is an example. Here is my function. Y is function of x. Along the graph, we have y equal to f of x. If I want to identify the region of the plane where y is less or equal to f of x, I must look at the points that lie below the graph, okay? Now, consider the set of points of the plane that are below the graph, this shaded area. This is clearly a convex set. Can you see that? Because if you take any segment, joining the points lying in this shaded dashed area, capital A, you see that the segment is fully included in the same set. So this is a convex set. So basically, the definition says that take the graph of the function. The function is concave if you take the set of the points that lie below the graph. If this is a convex set, then the function is concave. So this is the definition. So basically, the right function here, the black graph here is of a function which is convex. Why? Because minus f is concave. Okay? But you could also give a similar definition for convex functions. Just replace this inequality. A function is convex if the set of points that lie above the graph is a convex set. For the black graph, you take the set of points that lie above the graph. This is a convex set. Thus, the function is convex. But it is easier to just define concavity and just say state that convexity. We have convexity when the negative of the function is concave. This is the graphical interpretation of this definition. Okay, I don't want to waste time with this. With these two slides. This is just a summary of the basic. Remember that in the first two classes we reviewed the elementary functions, okay? This is just some computation to show whether the elementary functions are increasing or decreasing and are convex or concave by using the second derivative. The most important thing that you have to keep in mind here is that a power function, capital A times x to the power of alpha, with alpha between 0 and 1, is a strictly increasing and concave function. Of course, you can realize this immediately by computing the first derivative. First derivative of this one would be strictly positive in this particular case, and the second derivative would be negative. Negative means that the slope, second derivative negative means that the slope is decreasing. And you see here that the slope starts with, for these functions, the slope at 0 starts vertical. It's plus infinity, basically. It tends to plus infinity. Then, as you increase x, the slope becomes still positive, but flatter and flatter and flatter. So the slope is positive, but decreasing. The function is concave. And this power function is very popular to represent all of this, let's say, economic phenomena that imply saturation, okay? For instance, if this is a utility function, here we have decreasing marginal utility. If If it is a production function, here we have decreasing marginal product and so on. I mean, if you double the amount of the input factor when the input factor is very low, you have a strong effect on output. This is the idea. But if you add the same quantity, for instance, 2 units, when the amount of input is already very large, so the marginal change in the output is smaller, okay? So this is the basic idea, saturation. That's the way why it is used so often. Then there is some considerations about the logarithmic function and the exponential function. I suggest to have a look at these slides and just try to compute the first and the second derivatives of this function and evaluate its sign. Just realize that we have concavity or convexity according to the cases, okay? For instance, the exponential function, exponential of x, is increasing and convex. Exponential of minus x is decreasing and concave. The log of x is increasing and concave, okay? Elementary functions. We will use this later because we still don't know very well what a composite function is, but remember that these are two useful. I will review them again, recall them again when dealing with two variable functions. These are two very useful properties of concave functions. Sometimes it is not very easy to check for concavity, okay? But we have properties that help us with this task. If I have the sum of two concave functions, because they are elementary functions and I know the concavity of each of them, I can state that the sum of this function is also a concave function. This is a very useful property. And another property is this one. It relates to the idea of composite function. If we have the composition of two functions that are both increasing and concave, then the resulting composite function is also increasing and concave. We will review this later because it's very useful to compute the second derivative of a composite function of one variable. So I will use this, I will prove this by just computing a derivative, okay? Which, by the way, is an exercise on computing a second derivative of a composite function. But remember that we must arrive to the two variable functions because all of these concepts then are adapted to two variable functions. We have also nth order derivatives. I will never, this is just to complete the set of the slides. I will never ask you to compute third, fourth derivatives of functions, okay? But there are some simple cases in which it is possible to show the structure of the derivative of any order, okay? For instance, for the case of the exponential function, for the case of the power function, it's possible to compute, to have a general formula for the nth derivative of order n. But this is not really important. Just look at the notation because it may happen that you find higher order derivatives in your, at least when you, I mean, if you study an applied model, then you have just at least to understand what the notation is, okay? And this is the notation for the nth order derivatives. What is really important instead is the polynomial approximation to the second order, and I it's just 3 slides, but I will focus a bit longer on this because it is really, really important, because the same formulas basically apply also to two variable functions. Usually, in many kind of application, economics, but also other fields, we make approximations to functions near a certain point. Also, if you want to get analytical results that are easily interpretable, okay? So, for instance, what happens if I change a little by current level of output, current level of input, what happens to my output, okay? We use polynomial approximations. In many cases, we use linear approximations, the derivative and the differential, okay, over one variable function. In other cases, we need second-order approximations. So I want to show you how we can approximate a function up to the second order. In principle, we have nth-order approximations. We may have third-order approximation, fourth-order approximations. The larger is the degree of the polynomial that you use to approximate a function near a point, the closer is your approximation in general to the true behavior of the original function. So in the limit, you construct the same graph of the function. If you take n large enough, n is the order of the approximation large enough, in the limit you can perfectly get the graph of the function, not just near the point, also very far from the point itself, okay? What really matters for applications are linear approximations near a point and quadratic approximations. Quadratic approximations are also called second-order approximations. They are also called second-order Taylor approximations. And the formulas that you will see is the so-called Taylor's formula for a second-order approximation. Take the cubic root of x. We want to approximate this function. Approximate means replacing the graph, the original graph, with the graph of a polynomial, linear or maybe quadratic, near a certain point. We are interested in the point a equal to 1 of the domain, okay? 1 here. We already know what the first order approximation is, because we studied first order approximations already. We know that f of x can be approximated by a straight line near the point. Of course, if we change our point, I mean, this is point 1 and this is the blue one is the linear approximation. If I change my point, of course, also the linear approximation changes, okay? Because I must use the slope at that particular point. Anyway, in order to arrive at the first order approximation, I need to compute the first derivative of this function. This is x to the power of 1/3. It's a simple power function. Okay? So the derivative is 1/3 times x to the power of -2 over 3. Okay? What happens when x is equal to 1? If x is equal to 1 here, the slope is 1/3. Okay? So f prime of 1 is 1/3. Then we know that the linear approximation works in this way. I can approximate the function with the value of the function at the initial point, which is 1, because here, if you replace x with 1, you get 1. So f of 1 is 1, plus slope at the point 1, which is 1/3, times x minus the abscissa of our point, x minus 1. So this is the general formula. F of x can be approximated to the first order by f of a, of course near point a, by f of a plus f prime of a times x minus a. Okay? This is a straight line. In order to see that this is a straight line, if I don't like this form, I can just multiply 1/3 by x. And then here I have minus 1/3 plus 1 is 2/3. So I get 2/3 plus 1/3 x. This is the equation of a straight line with slope 1/3 and intercept 2/3 here. Okay? Now, what about a second order approximation? Here I replaced my function with a straight line. I want to replace it with a parabola. I need to compute a second derivative. So what is the second derivative of this function? Well, the first derivative is this one. So 1/3 is a constant, a multiplicative factor, times the derivative of x to the power of -2/3, which is -2/3 times x to the power of -5/3, okay? So if I multiply by 1/3, I get -2/9 x to the power of -5/3, okay? And this is the second derivative. I must compute also the second derivative at the specific point. You see that the second derivative is negative, by the way, because the function is concave. Must compute the second derivative at the specific point, which is -2/9, when x is equal to 1. Then the formula is like this. Next I will show you why the formula is like this, but the formula, of course, if I want to obtain a parabola, but at the same time, this must be the best linear approximation, my parabola will only add, let's say, starting from this, will only add a second order term that improves this estimate, okay? This is what happens. My parabola will add to this a second order term of the type x minus 1 squared. Okay? In fact, I will complete the exercise in a moment. When we want to provide a second order approximation to a function near a point, near point A, we call this approximation P2 of x, just to denote that this is a second degree polynomial. Our function, a second degree polynomial, can be written in this way. Capital A, a constant, plus b times x minus a, plus c times x minus a squared. Okay? So we have a constant term, a first order term, b times x minus a second order term, c times x minus a squared. This is not written in the usual way, but it's clearly a parabola because you can get here bx minus ab. ab is another constant that adds to the previous constant. Here you have x squared minus 2ax plus a squared, every term multiplied by c. So you have another second order term, a first order term, and another constant. So this is the best way to write it when dealing with approximations. The variable is not x, it's the difference between x and the point, okay? It's the deviation from the point, the variable to use here to get an easier formula. So I can write this in this way, but the point is that how can I determine the coefficients a, b, and c? What we want, it's very intuitive. I mean, we don't need to be mathematicians to understand what is the strategy to obtain the best second order approximation. When I approximate with a straight line near a point, I want to find a straight line that satisfies these two conditions. This must be an approximation, right? It must be the best linear approximation. Clearly, it is the tangent line at the point, okay? It must, as a minimum, the approximation must have the same value of the function at the point, okay? As a minimum, it must have the same value of the function and the same slope. So the best linear approximation is a straight line having the same value of the function at the specific point and the same slope, okay? The best second order approximation, the best parabola that approximates our function near a point must have the same value, the same slope at the point, and the same, let's say, level of concavity or convexity, which means having also the same second derivative, okay? So the strategy to understand what, to find parameters a, b, and c that characterize the best second order approximation is just to impose that the value of the function at the point is equal to the value of the polynomial that approximates the function. The derivative at the point is equal to the derivative of our polynomial, and the second derivative is also equal to the second derivative of our polynomial, okay? If I impose this condition, polynomial has this expression. What is the value at the point of the polynomial. If x is equal to a minus a is 0, a minus a is 0, what is left is capital A. So the value of the polynomial at the point is capital A. Capital A must be the value of the true function at the point, okay? So capital A must be equal to P2A, okay? So P2A is capital A. Capital A must be equal to P2A, which is equal to the value of the function. So the constant is the value of our function at the point. What about the slope? We must compute the slope of this polynomial. This is a constant, it disappears when I compute the derivative. This becomes B, okay? And this one becomes 2c times x minus a. But at the point, this term that includes x minus a disappears, okay? You see here. The first derivative of the polynomial at the point is just b. So second message, a must be the value of the function at the point, b must be the slope of our original function at the point. What about c? What is the second derivative? It is the derivative of the first derivative. So it is 2c here. So this means that the second derivative of the polynomial, we know that we want it to be equal to the second derivative of the function. This means that c must be equal to the second derivative of our function divided by 2. Okay? So don't make mistakes with second order approximations. The coefficient of x in the linear approximation is the slope. Okay, this is quite natural. And the coefficient of x minus a squared, this c here, is not the second derivative, is the second derivative at the point divided by 2. Keep this in mind, okay? And this means that the polynomial that approximates our function is f of a plus f prime of a times x minus a plus 1/2 second derivative of f at the point a times x minus a squared. This is the best parabola that approximates our function near x equal to a. The first two terms are the first order approximation. You see, the first two terms are just the first order approximation. This is an improvement of the approximation that takes into account the fact that the function is also concave or convex. In fact, when the second derivative is negative, that is, when the function is concave, the additional term, the improvement, subtracts something from the first order approximation. Okay? When the second derivative is positive, which means that the function is convex, it adds something to the first order approximation. And is that clear graphically? It's just a matter of, we don't need any formulas, we just need a graph. Okay, this is concave. Take point A here. The best first order approximation is this straight line. However, what happens, since the function is concave, when I use, suppose that I want to evaluate what happens to my function when I just deviate from A on the right or on the left. I add something or subtract something to A. Clearly, if the function is concave, the first order approximation overestimates the change of the function, because the graph, since the function is concave, the straight line lies above the graph. If I want to correct the approximation with a second order approximation, Since the second order approximation will include a negative second derivative, I will subtract something. I will improve my approximation by reducing a little my estimate, okay? Vice versa, if my function is convex, like this, and I just use my first order approximation, I underestimate the change. If I measure the change along the straight line, I underestimate the change starting from point A. But since it is convex, it will have a positive second derivative, and by adding the improvement term, I will partly recover this underestimate, okay? By adding a positive term. And this is the basic idea behind the second term that you see in the approximation here. Because this is always positive. X minus a squared is a positive term. So the sign of this last term depends on the sign of the second derivative. It is negative when the function is concave. It is positive when the function is convex. Now this is the improvement to our approximation. Here is an example, two examples. Just two examples. A cubic root of x. We already know what the first approximation is near x equal to 1. We computed it before. It's 1 plus 1/3 x minus 1, okay? Now I want to add my second order improvement term. Remember what the second derivative was? Minus 2 over 9. Remember that the coefficient must be the second derivative divided by 2, okay? So minus 1 over 9. So use the second derivative divided by 2, minus 1 over 9, times x minus our initial point squared. This is the second order term. In general, if we solve some exercises, we see also for two variable functions will be more or less the same. When we use when we approximate, we don't need to solve this for x, right? X squared minus 2x plus 1, and then multiply by 1 over 9, and then add the constant to the constant and the first order terms. We just leave this in this way, but we can compute very easily, solve some numerical examples and see that it works. This is the general formula with a equal to 1, and this is our example. For instance, approximate to the second order the cubic root of 1.06 without using the scientific calculator. The true value, approximate, there is important information missing here, near the point, approximate numerically this quantity. How can we solve this problem? By using polynomial approximations. I can look at this function, the cubic root of x, and then select a equal to 1, which is sufficiently close to this value of x, okay? And then try to approximate quadratically, linearly and then quadratically, our function near a equal to 1. And then use the approximation to compute 1.06, okay? So I select a equal to 1, which is a convenient starting point for our approximation. Also very easy for the computations. My x is 1.06, but remember that I have to express x, I had to use x minus a in the formula, and x minus a, if a is equal to 1, is 0.06. So I regard my 1.06 as a deviation of 0.06, which is small, from the initial point 1, okay? I will use 0.06 here and here. It becomes, the first order approximation becomes 1 plus 1/3 times 0.06. 1 plus 1/3 times x minus 1, okay? Which is 1.02. This is already very close to the true value, which is 1.0196. However, as expected, it overestimates the true value, because the function is concave. Then I add the second order term. How can I add it? I just have to compute the square of 0.06, which is 0.0036. So the second term is minus 1, the second order additional term is minus 1 over 9 times 0.0036. And this becomes 1.019600, which is basically equal up to the fourth position after the point. It's equal to the true value. Here is another example. In many applications, we look for approximations near the point x equal to 0. Okay? In many applied problems, it's very convenient to approximate the function near x equal to 0. For instance, for the square root of x plus 1, I want to approximate my function to the second order near x equal to a equal to 0. Okay? And so you can just compute the first derivative of this function. This is an example. I leave this example to you as an exercise. You have to compute, to apply this formula, basically. Remember that here, this is the formula for the second order approximation. As a byproduct, you will also obtain the first order approximation, which is the first two terms. Remember that we want to approximate around near point A equal to 0. So this is even easier formula, because A is equal to 0 here and here. So we will have x, and we will have x squared here, okay? Because A is equal to 0. We have to compute the first derivative and the second derivative and the value of the function at the point 0. Just compute the derivatives, evaluate the function, the derivative and the second derivative at the point 0, apply the formula, and you get this expression here. So the linear approximation is 1 plus 1 half x. The quadratic approximation is 1 plus 1 half x minus 1 over 8 x squared. Just to conclude, the first part, I want to show you what happens with the first and second order approximation for that particular function that I left as an exercise. Okay, my function, can you see? Yeah. My function square root of x plus 1 is the blue one, so it's this one. It's not very clear because it's quite flat at the point. It is the blue one, okay? The first order approximation near the point 0 is the green straight line. The second order approximation is the red parabola, okay? And if you enlarge this, you see that, if you can move on both sides, and for a certain range, the second order approximation is much better than the first order approximation, okay? It almost overlaps to the true graph, just for a certain range, because of course, this is not, it may be counterintuitive, but remember that these are local results, okay? So what is granted here is that the approximation improves provided that you remain in a small range, okay, around the point. Because for a parabola, a straight line is increasing, of course, in this case, and also our function is increasing. But the parabola at a certain point will go down, okay? So if you move too much far away from the point, of course, we cannot say that the parabola is a better approximation than the straight line, of course. But that's because these are local results. Okay? Is that clear? Of course, if we want to, what is the meaning of this applied in this example? If we need to approximate our function, which is this one, not close to this point, but close to this point, we will take a straight line and a parabola that pass through that point. Okay? We will approximate at a different point, not at this point, which is so far from the point of our interest. So this is the main message from this example. Okay, so I think that we can stop for about 15 minutes, and then we start with some introductory material on two variable functions. Okay, and tomorrow we will be able already to master differentiation rules for two variable functions, and also computing the same quantities, incremental, not the Newton's ratio, Newton's quotient, derivative, partial derivative, elasticity, log derivative, and so on and so forth. Okay. Right. Okay. Let's take about a 15 minutes break, and then we start with two variable functions. We take a 15 minutes break, 15 to 20 minutes break. Okay? Okay. Okay, start again on the basics of multivariable functions. Can you hear me? Is everything okay?
Yes.
Okay.
Yes.
Okay. So you should also be able to see the slides on the main screen. And there is a problem with the camera, so sometimes I disappear, but that's not a big deal. Okay, so this is about multivariable functions, in particular two variable functions. Two variable functions means that we have two independent variables or free variables. They can be chosen freely in the domain, but once we choose them, we have a unique value for the dependent variable. And this is computed through a formula, which is f, basically, the function. So usually we denote x, y as the independent variable and z as the dependent variable, or more often, this is typical for the case of two variable functions. This is more general. Y is the dependent variable, and x1, x2, x3, x4, etc. are the independent variables. So we can use both of them for two variable functions. And in general, if we want to denote a multivariable function, we use this notation: y is equal to f of x, where x is a vector with n components, because there are n independent variables. It is denoted in this way. In the textbooks, it is an x written in boldface. And an alternative notation is to underline the x to denote a vector. A vector is an ordered list of numbers, of real numbers, okay? We call the vector x and belongs to Rn. R is the set of real numbers. R squared is the set of the points of the plane. Each point has two coordinates, okay? So each point is basically a vector, so a list of two elements, of two real numbers. R3 is a point in the three-dimensional space, because in the three-dimensional space, every point has a list of three coordinates, okay? And so on and so forth. After n equal to 3, of course, we don't have the geometrical and intuition anymore of what the space is, okay, including the points, but of course it is a more general model, and in most cases we have two variables or three variables. So what is the meaning of f of xy? It just assigns to each pair xy of real numbers a unique real number z. These pairs of real numbers xy are selected in a given set, capital A, which is a subset of the plane, subset of R squared. Okay, so the domain, the important message is, be careful. The domain of a one variable function is the real line, in the most optimistic case, or a set of intervals, okay, on the real line. The domain of a two variable function is a portion of the plane, or maybe the whole plane. The whole plane or a portion of the Cartesian plane. We don't have intervals for two variable functions. We have subsets of the plane. This is the basic idea. Just a couple of examples to show you what the domain is for a two-variable function. What the domain of a two-variable function is, and also the range of a two-variable function is. Remember that the range of a function can be an intuitive idea of the range is let the point range into the domain, let the independent variables range into the domain of the function, keep track of all the points generated by the function, you get a set of real numbers, okay? And this is the range of the function. The range is also called image set of the function. If you take, for instance, this simple function, it's the log of a linear function of x and y. Z is the natural logarithm of 1 plus alpha x plus beta y. I will use this for some examples. Also in optimization, I will use this kind of functions, simple elementary functions. It's a simple composition of the log and the linear function of x and y. I suppose that parameters alpha and beta are positive, strictly positive, but can be any positive number. If I want to get a geometric representation of the domain, I must solve an inequality, because the domain, I mean the argument of the logarithm must be strictly positive. But the argument of this logarithm is a linear function of x and y, so I must impose that the quantity 1 plus alpha x plus beta y is strictly positive. If I write here 1 plus alpha x plus beta y equal to 0, I obtain a straight line in the plane, written in implicit form. Remember lesson 1, straight line in implicit form. But if I write a corresponding inequality that can be greater than, less than, or greater or equal to, less or equal to, basically the solution is not a straight line, is a half plane. So the straight line divides the plane into two parts, two half planes. And in one of the half planes we have the greater than sign, in the other one we have the less than sign. If we include also the straight line, we may have also equal here. So in this particular case, I can solve explicitly, but I have an inequality. Beta y is larger than minus 1 minus alpha x. Beta is positive. I suppose it is positive. I can divide by beta, both sides. So I preserve the sign of the inequality. Y is greater than minus alpha over beta x minus 1 over beta. It is a straight line. If I add equal here, this is a straight line in explicit form, okay? This would be the intercept, minus 1 over beta, this point here. And minus alpha over beta would be the slope. Of course, here the slope is negative because alpha and beta are supposed as positive number. So you see, you can represent this. It crosses the vertical axis at the point minus 1 over beta. The horizontal axis is, you can put this equal to 0. And you solve, you get that the intersection with the horizontal axis is minus 1 over alpha. Okay? Which is also a negative number because alpha is positive. So we can be very general. I mean, the shape is this one. Then if I change alpha and beta, what changes is just the intercepts here. But they remain both negative. And the area where y is larger than this quantity is above the straight line. So basically, this is the graphical representation of the domain of this function. So this function is not defined below this straight line. You cannot select any pair xy, but only those that satisfy this inequality. Basically, for two variable functions, we can figure out graphically what the domain is in some simple cases. While in the case of one variable function, we generally obtain an explicit form for the intervals, right, of the domain. Here, we can. It's much easier to figure out it graphically. Okay, so this is the basic idea, an example of what the domain is. Here is another example of what the domain of the function is. If I have a function like the square root of 1 minus x squared minus y squared, again, the argument of the square root must be non-negative. And this means that okay? And this means that this quantity must be greater or equal to 0, which means x squared plus y squared less or equal to 1. Since x squared plus y squared equal to 1, basic analytic geometry is the equation of a circle, basically, okay? So this region identified by less or equal is the inner part of the circle plus the boundary, okay? So the domain of this function is any point lying into this circle or on the boundary. There is no, I can compute the value of the function by selecting x, y outside the circle. So basically, just look at the range here. Here I write that the range of the function is any real number. It's easy to see why, but in general it's difficult to figure out what the range is of a two-variable function, and even for a one-variable function. But for a one-variable function, we can represent the function, and we see immediately the range on the vertical axis. For a two-variable function, that's much more difficult, okay? But in this case, the range is the whole set of real numbers. I mean, this function can take on any value from minus infinity to plus infinity by just selecting suitable values of x and y. Why? Because when we are very close to this straight line, the argument is very close to 0, because the equality 1 plus alpha x plus beta y equal to 0 is satisfied only on the straight line, okay? So when we are very close to this straight line, the argument is very close to 0. We can make the argument to be close to 0 as close as we want, okay? And this means that the log of a number which is very positive and very small can be negative very large, okay? So we can make the log as large as we want by selecting the point in the domain sufficiently close to the straight line. But on the other hand, if we increase x and y to very large numbers, then the log becomes also very large, okay? So the range is the whole real line, it's the third axis, okay? You will see the representation of our two-variable function. It has two axes to represent the domain, the plane, and then there is a third axis to represent the value of z. Okay, so in this case, for instance, the domain is the closed interval 0, 1. It's not difficult to figure out why, but this is not part of the exam. There will be no questions on the range of a two-variable function. What is really important here is the concept of partial derivatives for a two-variable function. Derivative is a measure of change. For one-variable functions, we have an initial point, an initial value for the independent variable. We suppose a small change around this point. And we compare the change of the independent variable with the change of the dependent variable. We basically take the ratio. Then we restrict the interval where we take this ratio and we get the derivative as the limit. In the case of two variable functions, we may want to start from a given point which has two coordinates, x0, y0, for instance. What is the meaning of assuming a small change, a small deviation from this point? For one variable function, we can have a positive deviation or a negative deviation, okay? But here we can have deviations along any direction. We just move away from this point in the plane. So basically the theory of partial derivatives and of differentiation of two variable functions starts from two main directions. One is the direction that I obtain by keeping y, the value of the second independent variable, fixed at the level of the initial point. So y will remain equal to y0, and I will assume a change of x, okay, on the right or on the left, starting from the level x0, okay? And this is one possibility. By doing this, I can construct the ratio between the change of the independent variable and the change of the function. I take the limit, and I have the partial derivative with respect to x, because y is fixed. Alternatively, I can take x fixed at the level x0, just change y, so moving vertically in this plane. Of course, if I move the point in the domain, the value of the function will change, okay? And I take the ratio between the change of the function and the change of y, basically, for a fixed level of x at the level x0, and I will take the limit, and I will have the partial derivative with respect to y. I've tried already to give you the formulas on the fly when we were discussing the derivatives of one function, one variable function. I wrote also the formulas for the derivatives of two variable functions, because they are basically the same. They are treated, when we compute partial derivatives, we treat the two variable function as a one variable function. We start from a point, we just focus on one coordinate in the plane, and we fix the other one. Then the function becomes a function of one variable, and we can define its derivative as the derivative of a one variable function. So the partial derivatives are in fact derivatives of a one variable function. Each, however, depend on the particular point where I compute them. So they depend on the two coordinates of the point, okay? So they will be themselves functions of two variables. Because if I change the initial point, the partial derivatives will change in general. Okay, so I remember that these formulas, I gave you already these formulas. Anyway, assume a change in one variable only. For instance, assume that only x changes, while y will remain at the level y0. The increment of the function, the change of f, is f of x0 plus delta x, y0, minus f of x0, y0. So f of x0, y0 is the value of the function computed at the black point. F of x0 plus delta x, y0 is the value of the function computed at this red point in the domain, okay? Take the difference, the function will possibly increase or decrease, okay? Take the ratio between the change of the function and the change of the variable under observation, which is x. Okay, the change of x is delta x. This is called the Newton's quotient for a two-variable function. Take the limit as delta x tends to 0 of this Newton's quotient, and you get the partial derivative with respect to x computed at the point x0, y0. Now, these are numbers, x0, y0. Try to be more general, take a generic point xy, and you see immediately that this is a function, itself a function of x and y. Is that clear? This becomes itself a function of x and y, because if I change the initial point, both partial derivatives will change. The partial derivative with respect to y do the same, but now compare the value of the function at the green point with the value of the function at the initial point. Take the difference, divide by the change of y, which is delta y. You have the Newton's quotient, which is this ratio. Take the limit as delta y tends to 0, and this, provided that this limit exists, this is the partial derivative with respect to y. The two partial derivatives are defined and computed as derivatives of a one variable function, actually, by keeping the second variable at a constant level. But when I obtain the result, if I start from x0, y0, which is a number, I get a number here and a number here. But if x0 and y0, or x and y, are the initial point as a generic set of coordinates, the partial derivative will be itself a function of x and y. And this has an immediate implication on the rule that we use to compute the partial derivatives. Suppose that we have a two-variable function, f of xy defined by this formula. X squared y plus y to the power of 5. If I want to compute the partial derivative of this function with respect to x, I regard this as a function of x only. Y is written y here, but it is treated as a parameter. It's like a number. If you find it difficult to switch from one variable derivatives to two variable derivatives, just replace y with, for instance, I don't know, 2, okay? So that would be 2x squared, and that would be 2 to the power of 5. Compute the partial derivative with respect to x. Okay, you would get, this would be 2, okay? You would get 2 times 2x. But this is not 2, this is generic y. So we have y times 2x. So y is treated as a multiplicative coefficient of x squared. So its derivative is 2xy. It depends on both x and y. And what is the derivative of the second term of this sum? It is 0, because this doesn't depend on x, so its derivative is 0. Clear? Is that clear? Okay. The partial derivative with respect to y, now y appears in both terms, okay? So, with respect to the first term, the partial derivative with respect to y is x squared. This is the derivative with respect to y, so x squared is a coefficient now, it's like a number. It's like having 3y, the derivative would be 3. We don't have 3, we have x squared, so the derivative is x squared. Y to the power of 5, this part is only a function of a unique variable, so its derivative with respect to y is 5 times y to the power of 4. Okay? So this is just to show you how it works. It's just the derivative of a one variable function. You have to consider the other variable as a fixed parameter. And then there are more examples, and I can also show you before solving these examples, because I want to show you all the differentiation rules for one variable and the corresponding rule for two variables. So we will also show, I mean, if you are already familiar with the chain rule, which is the derivative of the function of a function, I can show you also this example. What is the derivative, partial derivative with respect to x of a generic function of two variables squared? Here, we must remember what the chain rule is. It's the square not of x, but of a function of xy. Anyway, it is a composite function, okay? First, I have to compute the derivative of this power with respect to the base, which is 2 times the base, 2 times f of xy. And then I have to multiply by the derivative of the base with respect to, in this case, to x. So it is 2 times f of xy times the partial derivative of f with respect to x. This is a simple example of a chain rule applied to a two-variable function. What is the derivative with respect to y? The first step is the same, 2f of xy times partial derivative of f, this time with respect to y. Okay, but let me just illustrate what the geometric meaning of the partial derivatives is, and then I will show you the basic differentiation rules, review of all the differentiation rules for one variable and two variable functions. They are already in the slides, so you don't have to write down anything, but I want to illustrate all these rules one by one. I mean, what is the meaning of what is the geometric idea of the graph of a two-variable function and the meaning of the partial derivatives. Okay, this is an example of a possible graph of a two-variable function. It is a surface in the three-dimensional space. The axes in the base plane are x and y. The orientation is this one, of course, because we cannot just take the usual Cartesian plane, because otherwise we cannot see the third axis. And the third axis is that if we select a given point x0, y0, this rectangular area is supposed to be the domain of the function. If we take a point x0, y0 in the domain, this is a point in the base plane. If you want to see what the image of this point here is, and so what is the point generated by the function from this point of the domain, we have to take a vertical straight line until we cross the surface that represents our function, and then pick the corresponding value on the vertical axis. So this is the corresponding value for z, which we call z0. If you do that for any point of the domain, you basically get a surface in the space, okay? So the geometric representation of a two-variable function is, in general, a surface in the three-dimensional space, which is called R3. There are particular cases in which this surface has a very simple shape. For instance, it can be a plane. This is not a plane, of course, but it can be a plane. In this case, we would have a linear function of two variables. And what is the meaning of the partial derivatives? Okay, we have a surface. This is supposed to be a surface in the space that represents a two-variable function, okay? This is the usual point in the domain. There is a different orientation here of the axis. This is the x-axis, this is the y-axis, and this is the vertical z-axis. Take an initial point in the domain, x0, y0. Of course, when I compute a partial derivative with respect to y, I can only move in this direction, along the blue dashed line in the base plane. If I take the partial derivative with respect to x, I can only move in this direction, starting from the point, and along the red dashed line in the plane. Okay? If I move along the blue line in the plane, okay, it's like, imagine that you build also a vertical plane that crosses the base plane along this line and is parallel to the plane YZ here. So you cut this surface, you would cut this surface, okay? And the cut would be this curve here, okay? This is a one-variable function, okay? Then you are measuring the slope of this surface along this curve. Okay, this is the partial derivative with respect to y. If you cut the surface with a plane which is supposed to be parallel to the plane xz, you get the red curve on the surface. Okay, this would be the cut. Okay, along the surface with the vertical plane. If you measure the slope along this red curve, you get the partial derivative with respect to x. I hope this is clear enough. Anyway, this emphasizes why you are in fact computing derivatives of a one-variable function, okay? You are computing derivatives along a curve, not really along a surface, or along a surface in a given direction, which means computing derivatives along a curve. So this is the meaning of the two partial derivatives. You see that they may have very different slopes. Suppose that you repeat this experiment here, point here, you would have very different slopes for the two partial derivatives, okay? So this is why the two partial derivatives are themselves functions of the particular point in the plane that I select, x, y. Okay. So I would like to switch now to a summary of the rules of differentiation for one variable and two variable functions, and then show you a number of significant examples, very useful for economics. Okay, so let me just switch to another set of slides. This is the last chance to refresh the differentiation rules also for one variable functions. Okay? I tried to build some slides. On the left side there is a one variable function, on the right side there is a similar function with two variables, just to see how the derivatives compare to one another. Okay? A constant function of one variable has a zero derivative. If I have this function, this is a function of one variable, but it is regarded as a function of two variables. This may happen in applications, okay? We have a one variable function, but it is regarded as a function of two variables. What is the partial derivative of this with respect to y? It is zero, because it doesn't depend on y. Also, that could be x plus a constant. If I take the derivative with respect to y, it is zero. Take a linear function, for instance, f of x is mx plus q. The derivative is the slope m. What about a two-variable function of linear type, mx plus ny plus q, okay? It's like having two different slopes in one direction and in the other direction, okay? What is the partial derivative with respect to x? It is n. The partial derivative with respect to y, it is n, okay? Just to show you how it compares with the basic case of one variable. Now take this function f of x of one variable is a linear combination, is a constant plus a coefficient times another function g of x. Generic one variable function g of x. What is the derivative? F prime of x is the constant disappears, and it is the coefficient a times the derivative of g. Okay? A g prime of x. Do the same with a two-variable function, a constant plus a coefficient times a generic two-variable function. What is the derivative of z with respect to x? It's like this one. A constant, times the partial derivative of g with respect to x. The same idea that we have in the one variable case. And also, what would be the partial derivative with respect to y? It would be a times partial derivative of g with respect to y. This is called, we can say, I use partial derivative of g with respect to x, but this is also, I can also call it dg by dx, okay? This is a different symbol. It's not actually d, because d is the symbol for the derivative of a one variable function. This is the symbol of the partial derivative. Okay, this is an example with power functions. You will see later that power functions are called isoelastic function because they have constant elasticity. This will hold for both one variable functions and two variable functions. If I have the one variable function constant capital A times x to the power of r, or alpha, I don't know, we call this alpha sometimes, where the exponent is any real number, and of course x is a positive quantity. Remember when we discussed the basic power function, x is supposed to be a positive variable. Its first partial derivative, this is a one variable function, is just a constant times, what is the rule for the power function? The exponent becomes the coefficient r that multiplies the same variable x to the power diminished by 1 unit, r minus 1, okay? In the case of a two variable function, for instance, this is an example with one variable, x to the power of 3, the derivative is 3 times x squared. 1 over x, which is x to the power of minus 1, its derivative is minus 1 times x to the power of minus 2, which means minus 1 over x squared. Now, pick an example with the two variables. 3 over 2 times x squared y to the power of minus 1/3. This is a typical example of a two variable function of power type. We must have only products between the different quantities, not sums, products, and we have possibly a constant, a multiplicative constant, times a power of x times a power of y. Okay? This is a power function in two variables. What is the derivative? It depends on which variable we are taking the derivative. The derivative of f with respect to x is y is regarded as a constant. The power of y is regarded as a constant. So it is 3 over 2 times 2x times the constant, which is y to the power of minus 1/3. This is its derivative. Partial derivative with respect to y. Now I regard x as a constant. So it's 3 over 2, which is our constant, multiplicative constant, times x squared times minus 1/3 y to the power of minus 4 over 3. Clear? So then I can simplify. It's minus 1/2 x squared y to the power minus 4 over 3. Okay, another example here is 1 over 3 square root of x is 1/3 x to the power minus 1/2. Its derivative, in the case of a one variable function, is 1/3 times minus 1/2 times x to the power of minus 3 over 2. So it has this final expression, okay? So you can, change the exponents here and try to practice a little bit with these derivatives. You can take this example here with a one variable function and then add times y raised to a given power, and then try to compute the derivatives of these two variable functions. Of course, all of these rules can be combined together. For instance, if I have a two variable function which is 3 plus 2, 3 plus a power function plus y, I take the derivative of each term and I take the sum, because the rule of the sum always holds, okay? So the derivative of the sum is a sum of the derivatives. I prefer to show you by examples and comparison with the one variable case. So the derivative would be, in this case, 3 disappears here, 2 times, remember that we are taking the derivative with respect to x, so it is 2 times 3x squared times square root of y, because it's like a constant, plus nothing, because we are taking the derivative with respect to y. And this is the final form of our derivative, okay? I hope this is clear enough. There is nothing difficult. I don't waste time here. We have the rules, the sum, product, and quotient rules carry the same, carry to the case of two variable functions without any change. This is, for instance, the quotient rule applied to a one variable function, and this is an example with a two-variable function. For instance, if I have a function defined in this way, nominator 2x plus y, a linear function of x and y, denominator square root of x. I can regard this as a quotient, but also as a product. Okay? So I can compute the derivative, for instance, the partial derivative with respect to x, using both the product rule or the quotient rule to obtain the same result, of course. This is a useful exercise. The partial derivative of z with respect to x, regarded as a product, that would be the derivative of the first factor times the second plus the first factor times the derivative of the second with respect to x, of course. So the derivative of the first factor with respect to x is 2 times the second factor x to the power minus 1/2 plus the first factor 2x plus y times the derivative of the second factor with respect to x, okay, which would be minus 1/2 x to the power minus 3/2. I can also compute it as a quotient, because I can regard this way. So, the quotient rule, just take the denominator squared, which is x, and then the derivative of the nominator times the denominator, 2 times square root of x, minus the nominator times the derivative of the denominator, 2x plus y times 1/2 x to the power minus 1/2. Then you can divide both terms in denominator by x, okay, and you obtain the same result as above, okay? This is exactly the same result. By exercise, just to see the difference. Here we have, let's say substantial computations, because both terms depend on x. But if you take the derivative with respect to y, then you see immediately that the second term doesn't depend on y. So you don't need to use the derivative of a product or of a quotient. Just look at this one as a constant, and you have to compute only the derivative of this one, okay, times the constant. Of course, if by mistake you use the quotient rule or the product rule also when you compute the derivative with respect to y, in principle you're not wrong, because it is a product or it is a quotient. But you don't need to do that, okay, because this is not in fact the product between two terms depending on the variable, because the second doesn't depend on y. So the derivative, for instance, with respect to y is just square root of x, okay? Because it is square root of x times the derivative of this with respect to y, which is 1. So just try to just write down functions of two variables. In some cases, sums, products. In the products, try also to put terms that do not depend on one of the two variables and compute the two partial derivatives. This is a useful exercise. Okay, so maybe we should stop here. Maybe. Let me see. Let me just show you this example, very quick example. This is the most popular function in basic microeconomics and intermediate microeconomics. This is the most popular function. This is a power function in two variables, often treated in a slightly general manner in which the exponents are not specified, but they are left as parameters, okay? The power function in two variables is called Cobb-Douglas function, especially when the exponents are between 0 and 1. It is often used as a utility function with two goods or a production function with two input factors. This is called Cobb-Douglas function. It's very useful as a final exercise for today to compute the partial derivatives of a two variable function like this and to express the two partial derivatives in a slightly different manner, which is very useful for applications. So the function is a positive constant, capital A, times x to the power of alpha times y to the power of beta. Capital A is usually positive. For instance, if it is a production function, the coefficient capital A is positively related to the level of technology. X is the amount of one input factor, y is the amount of the other input factor, and these exponents are usually positive quantities, usually in most cases between 0 and 1. What is the partial derivative with respect to x? It is capital A, so y to the power of beta remains constant as a multiplicative factor here. Capital A times alpha x to the power of alpha minus 1, which means that the partial derivative with respect to x is just alpha over x times the value of the function. Why is that? Because you see that the derivative with respect to x has a structure which is very, very similar to the original function. Okay? It's again a power function in two variables. What are the only differences? In the derivative, there is the additional multiplicative factor alpha, which was the exponent of x. We are taking the derivative with respect to x, okay? There is the additional multiplicative factor alpha. The part on y is the same, but the part on x here has the exponent diminished by 1 unit, which means this one divided by x, basically, okay? So you only have the original mathematical expression, which is the function, times alpha, which is the new multiplicative factor, divided by x. Okay? This is a very useful expression for a number of reasons. One, when you want to compute the log derivative, you have to take the ratio between the derivative and the function. So the log derivative is already here, alpha over x. This is also related to the elasticity, to compute the elasticity, for instance. Second, when you solve constrained maximization problems in which this is the part of the objective function, it's very useful to express the partial derivatives in this way, because you can find the optimum much easier, in a much easier way, if you express the derivative in this way, okay? For the solution, if you remember this, that's the trick, this alternative way to write the partial derivative, this turned out to be very useful. The partial derivative with respect to y is exactly the same as before. Now x to the power of alpha remains constant. We have the coefficient beta that multiplies y to the power of beta minus 1. And this means that you can write the partial derivative with respect to y as beta over y times the value of the function. Okay? Well, this is a very useful way to characterize the partial derivatives of a power function in two variables. Okay, so I think that that's really enough for today, and see you tomorrow morning at 9:15. About the midterm, I just wrote an email to Professor Anna Montini, because if I guess that the November 4 is also the date of the partial midterm exam of the other course, right? Anna Montini's course. So I would like to change to make them in 2 different days. At which time is the midterm exam of Anna Montini? 10 a.m. So you would have 10 a.m. resource valuation and blah blah, and 3 p.m. mine. I'm trying to change the date of my examination. I just wrote an email to Anna. I didn't know that. I didn't know that. So, but they are not official. They are still unofficial. So, not public yet. Okay, thank you, and see you tomorrow at 9:15. Bye.
Bye.
Thank you. Bye.
Bye.
Bye.